Okay, good afternoon. You can hear me and see the screen. Okay, great. Then let's just get started. So we're going to talk about model training, hyperparameters tuning, and evaluation. So by now, you guys already are familiar how modeling works with these parameters are, which models have. So this is would be some notes to strengthen your understanding. You already done the evaluation, so you are familiar with the concept. So pretty much I will not be telling you something different, but hopefully it will strengthen your understanding of the whole thing. So as you know, model training is a process of feeding a machine learning algorithm with data. So it can learn patterns from those data and make a better prediction for whatever purpose you are training it for. So you provide the model with the features and label the target outputs and you train it. So it tries to predict the outputs that you going to be asking it based on the patterns that it understands so far. So types of model that we have in general, we have not the model themselves. We have millions of models around that exist. It's not about them, it's just a general model. We divide them in three ways. There is a supervised learning models, which inside of them, there are different types of supervised model that you can use. There are unsupervised learning and the reinforcement learning. So with the supervised learning, what differentiate them is the data. So supervised learning models expect a labeled data. So classification regression models usually uh, uh, just they are models that expect data sets that are labeled. So it is more easier. That's why the name is supervised. The data is already known, it's labeled, and the output is already labeled known. So it's the easier model learning. Those kind of models, we call them the supervised learning that accept labeled data. The unsupervised learning, it is those data set which you don't have labeled data. You don't know what that data really is. In this way, when you have that type of data set, you use unsupervised learning, which means you give the model to predict, uh, to make classification based on the pattern it is on the data. So like, you know, we give it a number, right? So based on those data, like k-means clustering and everything, what they do is they try to find some kind of mathematical relationship between those data points, and they gather those points that are, you know, uh, near to each other as one cluster, and so on and so on the other. So these models try to find some kind of relation and cluster them and understand some pattern to predict some output. This type of way of doing this data set, handling this data set, is called unsupervised learning. And the third one is the enforcement learning, which you teach by via reward signals. Like for example, yeah, robotics games where they learn if something is right, if they get the reward, so they will take that part. Then if I get rewards through this process, it means this way is right. So they try to understand those patterns and everything by reward system. Like when you teach a dog how uh, by snatching a food away from it, if it's barking too loud, it will understand not to do that, at least to other people. It depends on, this is the same way that dog trainers do. So they give it food when it's doing good or when they want to learn them how to sit, and they remove the food out of them to remind them not to do some things. So like that, reinforcement learning focus on learning these signals through reward. So these are automatic learning that happens within the reinforcement. That is another area. And with the point is models in general, we divide them in these three ways, and the trading of those data happen in different types, like I mentioned right now. So that's about model training. And when we come to hyperparameters, you have seen that the model that you use so far has parameters that you can customize, right? You can increase the estimator values, the number of iteration that it goes through. These are values that you can manually adjust when you feed the data to your model, and we call those parameters, hyperparameters, that are external knobs you set before training. So they can control how the model learns. Unlike regular parameters, which are learned from the data, hyperparameters are selected manually by the trainer, the developer. So hyperparameters are not directly learned within the model, but it is an input that the model gets to train the data. So examples like this, logistic regression, support vector machine, decision tree, these uh, models accept these inputs, these parameters that you can set before training the data, and we call them these hyperparameters. So hyperparameter tuning uh, needs, yeah, it needs a model, of course. It needs a parameter space. For example, if you are adjusting the maximum depths, there's a range that you can give it, right? You need to have which range should I, manipulate the data on to get a better performance. So the better you know what each parameter means, the better for you to guess which number you should give to see a better performance. This will come the more you do model training. It's just to save. You can randomly choose, of course, but the better you know what they meant. Where when you see different data's performance, you might be at some point professional on which numbers to pick. It's just by getting used to these trainings. So it's just parameter space. So when it's about maximum depth, knowing what maximum depths or other parameters, depending on the model, there are a number of parameters can exist. So understanding them will help you better to assign some ranges of numbers. A method for searching sampling candidates, cross validation scheme, and score function. This all things that is needed within the hyperparameter tuning. Why does this matter? Why does it matter? This hyperparameter tuning. So a model performance highly depends on the right hyperparameters. If you give it, for example, a large number and the data set is big, uh, and the data, how clean the data is another question by itself. But other than that, models can take a lot of time to finish those heavy data sets. So the better way when you have a larger data set is to break it down so the model learns each things easier than giving it more heavily loads. So this is depending on the scenario in the data site, that the data set value that you have, you can decide the weight the model can handle for processing them and understanding it. So too low or too high values can lead to underfitting or overfitting. So sometimes when we say overfitting, the model can perform really well. I mean, you gave it a small amount of data, or you gave it both the test and train data to train it, and when you test it through the test data again, it might give you the best performance. So that we call overfitting. That can be really misleading. But if you test it with a different data set that you haven't used on the training, you might see the difference. But these are scenarios that can happen. So they might come up really perfect with fewer data sets because the model is not trained for different patterns. So when you give it a different one, it will fail. But with those particular design sets, data sets, or without exact trained data set, it might come really doing a really good job. So at that case, we call them, if it happens to fail with other new data set, we will identify that model training, it was overfitting. So that's the definition of overfitting, when it comes really to really good with its performance, unless it's proven otherwise. That is. So the underfitting occurs when the machine learning model is too simple or too complex enough to capture the underlying pattern. So underfitting is it doesn't perform well. It didn't really get the training data patterns. It's really failing with that case. With overfitting, it's really good, but it has some questionable things when it is really good. So you need to balance these things. So these are just scenarios that happens during model training. that you should be aware of. So what are the methods that we can do with hyperparameter tuning? There is a grid search, there is a random search. So to change these parameter values, what you can do, there are already existing methods that you can do in addition to changing the each parameter values. What is the grid search? So grid search is like testing every possible combination. So for example, if the maximum depth range is 135, the grid search, what it does for you is it will create every the possible combinations so once we could have, and the model go through all each combinations with the grid search. So 135, it will take 1 and 1 and 3, 1 and 5, 5 and 3. So it will go every matrix values and it make sure every point is combined, and the model goes through each combination before it stops training. So at the end, it will give you the best hyperparameter values that you could use to train your model. That was grid search is. So it needs to go through with all the combinations before it turns out the best parameter that it find for the model to perform well, which is good. So whatever number you give it, it will go through everything and it will decide the best one at the end. The down part of this is it can be expensive. So if you have a few data sets, you might not notice it. But if you have a large data set, going through every combination to get the right hyperparameters the model is performing on can be really expensive because it needs too much computation power. But this is one of the methods to identify which hyperparameter values are best fit for the model. The other is randomized search compared to grid. This one is less expensive, even though this one touches every point, which is good. But with randomized search, you give it a fixed number of random combinations and it will pick any, it doesn't need to go every point. It will randomly pick some points and test the model performance and identify the base hyperparameter space. That's how it does it, to identify those parameter values, to pass it to the model, then train it through those methods. So to avoid, we have seen some comparison between the two. Still, we are taking a risk with random because it's taking too much, some points randomly. It might lose those parameters that can give you a better result because it didn't pick them through this randomized picking of numbers. So you are taking a risk with randomized search because it might not pick the right ones. With grid, again, it's costly to teach everything, especially with higher data sets. So one thing that we have that can solve the gap that we see between the two is the cross-validation technique, which is it. Okay, we'll go deep with it later after a slide. So training a model to make a prediction means learning the parameters of the model, and training and testing it on the same data is a mistake. Like you guys already have done a lot. You are splitting your data between test set and train set, and you are training it with the train set so you can evaluate it through the test set. So if anyone is here that is training the data with the whole data set, that is wrong. The chances are you're getting an overfitting result would be big. The model will be overfitting. So it might come, you might see it performing well because you have trained it with both test and train set. So likely when you give the train set, the performance would be more than 90% is higher. So you need to be careful which belongs to which. So we already discussed the definition of overfitting, but what we can do for what kind of issues that we're having with this type of this, how to avoid overfitting. So we can, to avoid overfitting, we can divide the training and test set like we said, and we can also divide the data into 3 sets: for training, for validation, and for testing in case of hyperparameters. So you can use a validation set to identify the hyperparameters, and then test it through the training and validation in combination, and then test it, evaluate it through the testing data. But what is the problem when you are doing this? One of the problem is you are decreasing the data set amount when you are dividing it into three splits. Even though it might solve some problems, you are causing another problem, that is the model is training with fewer data sets, which can cause data missing for the model. So one of the issues is dividing the data into three sets. Like I said, it will decrease the number of data set sample that you will be training it, and the result may depend on a particular random choice of the pair, either training or this is depending on your decision. The problem might occur, so you can choose after identifying the hyperparameters again to train the model by combining the train and validation sets together and evaluate it through the testing data. But there are risks that you are taking by following this mechanism. Just to see the flow, if we decided to break our data set into three, that is the training set, the validation set, and the testing set. Let's say we have split it like this. We have 100% data. From the 100%, we take the 60% for training, the 20% for validation, and the 20% for testing. So you try to identify the parameter tuning on the validation set. So after you're done with that, either with the grid or random search, and you identify the parameters that may help the model to perform better, then you combine the two, the training and validation set, and you train it again with both, just to increase the number of samples the model is training on. So now you are using more data for better learning of the model. So final evaluation, you evaluate the 20% set, which is the model doesn't know about, and see the performance. So with this way, you can solve the problem, but again, you are taking a risk with the issues that we mentioned before. So to avoid one of the two issues that you can see from this way of doing things is splitting into three means less data to actually let the model learn from. So it's just all of them that we just said. So to avoid this, one of the suggestions that can be that you can do is using the cross-validation technique for this issue. And the other issue that you might see here is random split might not be representative. So one random split of training or validation might give a bad split. So you are splitting it to 60, 20, 20%. So you don't know which information that you are taking on the test data, or you don't know what you are taking on the validation data. So you are taking a risk. You don't know, there may be some information that are lost that the model should have been learned on. So you might get some performance decline at the end. So there is some risk that you are taking by splitting the data set into different sections for the purpose that you are trying to accomplish. So your model performance might look inconsistent or unstable depending on the data and the use case that you are trying to accomplish. The performance might not come in hand at the end. So what is the other option that we have? You don't want to split the data, and if you want to still make sure the model learn from enough data, what you can do again is the suggestion is you can use cross-validation method. Now there comes what is cross-validation. So cross-validation is a statistical technique used to assess how well a machine learning model generalized to unseen data. So instead of relying on a single train test split, cross-validation helps evaluate model performance more reliably by using multiple splits of data. So there is multiple splits happening, but still all the data are used with cross-validation. So let's see here. With cross-validation, there are different types of cross-validation techniques. One of them is K-fold. This is just one of them. I have put a reference to read more on cross-validation that have different types of cross-validation techniques that you can use on your data and see the difference. But let's see this example, this particular careful cross-validation, how it works. So let's say you have a data, and what cross-validation does is it splits your data into 5 sections. For example, this 5 is something that you can assign from your side. So a user can assign how many folds that uh, the validation should have, the cross-validation. So let's say now 5 is picked. So it splits the data into 5 equal parts, 1 F2 F5. Then on the first iteration, when the model is going, so it's 5, it means it will go through 5 iterations before the model stops training. So on the first iteration, it will assume F1 is the test set, and it will train on the fives, on the rest of 5 folders. Then it will evaluate on the test set, and on the second test, it will take the F1 as the training set, and it will take the F2 as the training set, and it will train on the rest of the 4 sets, while taking this one as a test set, and so on until all the folders are ended being evaluated and trained, which means the model has all the information still being evaluated against that particular fold, which it continues the process until each fold is used exactly once as a test set. So final step, compute the average performance. It will compute the average performance that it gets from each iteration, and it will give you those metrics. And this is more reliable compared to the others because the model has all the patterns, and it's again testing it against the folders that it breaks. So it is more reliable, this way of doing it. Each fold has turned as a test state, which is all of them has been tested as a test state, ensuring a broad evaluation over different data splits. All data gets used before training set. All data gets used for both training and testing, but never simultaneously. They are not used at the same time, but they take a turn in being tested turn by turn. So this guards against overfitting. So overfitting happens when you test them both training and testing set at the same time. Overfitting happens, so which solves the overfitting problem that it might occur. That might occur. So this is cross validation in short. Just to see it in some visualization to make it easy. If you have the data, the old data, it break it the training data with the cross validation. In this case, with the k-fold cross validation, it breaks them with the folding value that it has, in this case 5, and it will create the test in the training set in different iterations until all of them take a turn and have that particular value. Then the average of those iterations would be the performance of that data set on that model, or the model performance for that particular data set. It will be provided as a final evaluation. This is how cross-validations works and helps to solve the overfitting problem. So if you go to this collab, just to see it in action. Okay, so I'm using a scalar until it runs. We can talk about the code. I'm using all the scalar functionalities here. I'm also on this particular one, I am using the make classification of scalar, which helps you to create a random data set, just to see the performance of the the cross validation. So Well, this one is also running. Let's just move to this one. So basically here it's creating imbalanced data set to see the difference between using before cross-validation value and after cross-validation value just to see some comparison. So here we pass the training set in the data's X and Y features. So here it is training. This is before without any cross-validation technique. This is a simple training like you guys have been doing it so far. And this on this one, we are using the K-fold cross-validation. We give it the n splits value. This one, you can adjust it as much as you want, this parameter. And after this, it's doing the K-fold algorithm behind the scene. So if you see here before without cross-validation, the accuracy and everything is good because it's good. And after that one, see, after the K-fold validation, if you see the accuracy score, on the first one, it's also good, but on this one, it's really good. On this K-fold, almost all of them are 95% and above. So you will see the difference because I'm not using an actual data. You might not see the difference, but this is already, it's likely that a good result will come up with the data sets that I just created with make classification, but still you can see the difference. Even if it's almost similar, it is a confirmation that the model is performing well compared to if with the K-fold, if you get some kind of similarity without it, it's a confirmation for yourself that some kind of assurance that the model is performing well, because even with those splits and a lot of combinations happening inside, being able to get good performance is a good sign. And here just to see the difference with a different data set, from the skill learn, I have loaded the load breast cancer dataset they have. This is a sample dataset that they can give you through the Skinner dataset library. So I have this breast cancer dataset has a malignant benign targets inside it to identify how many of the breast cancer users are in the benign level, which is the first stage, in the malignant level, their disease symptoms. So this is the targets to identify benign and malignant patients. So with this one, if you see again the same logic happen here, almost the with the both the evaluation is done on the test and evaluation. This is the whole output that you see here. Almost the model is performing really well even without the cross validation, and without the cross validation, and with cross validation, again if you see it, almost 90% and above is the accuracy score, which is really good. So it's a way to be really sure that your model is performing well, because cross validation does touch every data and test every data, not simultaneously, but unsimultaneously, and try to give you more reliable output. This is with K-fold, but you should explore as well. Here, if you go to this reference, this is the one that we just saw right now, the K-fold, where we have this the holdout cross, the Stafford. There's a lot of them, which the concept is the same, but the way how they handle the data split is different. So check them out and see which is better for your data set. These are all mathematical algorithms that break down as much as possible to get the right accuracy and to make sure the model address every data pattern. So hopefully you understand the idea behind cross validation of everything and so on. So to generalize, finalize everything that we talked about so far, how you can avoid overfitting, because it can be really misleading, is use regularization. This is add penalty to large model to discourage complexity and prevent the model from fitting. So regularization is a mathematical algorithm that you can You don't have to do it, the model does it, but it tries to regularize the data set as much as possible. So if there's too much weight, it will minimize it and so on. It does this regularization on your data set. So this is mathematical algorithm, like it just makes sure the like normalization, it tries to balance it out to avoid this overfitting with the noises and everything, which we have, especially if there are unclean data that can create the confusions, the hallucination and everything. It's not the perfect solution, uh, but it is one of the solutions. And choose simpler models, the other one. So use models with fewer parameters, example, linear regression over deep, to reduce the risk of overfitting, because with complex models, you need to be able to understand them really better with how you define those parameters to avoid those overfittings. So the simpler ones are simpler to adjust and simpler to deal with and to understand. So it might come like that, but depending on your need and data, you may not have a choice to use the simpler models, but this is one suggestion. Collect more training data. This has been said a lot, right? We have been saying this a lot. The more data that you have, the better for the model, because it helps it to understand different patterns with the data, which really helps to be aware when new data come in to evaluate those models. So the more data, the better, as always. Data augmentation, this is, for example, if you have a data set and if you don't have access or means to get more data, what you can do is data augmentation. That is, try to multiply that data set in different formats. For example, let's say it's easier to understand it. For example, if you have image data and you are training the model on those images, you can try to rotate the image and add it on the data sets. So if they are portrait, you can still it helps to understand model of different sizes. You can do some manipulation on the image if possible, and you can just try to multiply the data set in different angles as much as possible, as much as you can do. And that way you can have more data. And with text, the same with audio files. And if you have, you can if you have, for example, audio files, you can increase their speed. When those audio files have speaking, you can increase the models, the speed of those audio files. That is new data for the model. Or you can add some background noises to identify, to help models to understand what it means. You can just do some manipulations on your existing data set to create more data, to create more pattern that possibly help the model to see different patterns within the data. And with text data, you can also multiply it, not replace it. You are trying to multiply it. The existing one will still exist. You're just adding on it. With text data, you can try to replace, not replace, sorry, just create new ones with the same data. You can, instead, for example, if you are using the word amazing in a sentence in your existing data, you can choose it's the synonym of that one on the new data. So instead of amazing, it will use wonderful, so which means a new word for the model. So you can create these data augmentations to increase the data set's shape or size and have more training data. This is just tips that you can do if you don't have the access to those new data. And use early stop-based validation loss. This is stop the training when the validation performance stops improving, preventing the model from continuing to learn noises in the training set. So if you see some pattern where the model keep performing bad, it's just it might be different reasons. So instead of just letting it do, especially when you are using your money to train these models, you probably will stop it by yourself. But it's just one of the practices. If it's improving bad, it's just making more the model to learn unnecessary noises that happens within the given data. So it's better to stop it early. these are suggestions that you can do. There are more suggestions, but these are one of the common suggestions to prevent overfitting. And the other one is, like we said, do not train the data, pause on the train and test it at the same time. So it's likely going to perform really well when you are doing that, which is overfitting, not a good performance. We just will name it as an overfitting model if it's not doing the same performance when you give it a totally new data. So to summarize what we just talked about, hopefully you have understood me, is model training is a fundamental process of machine learning algorithm. Learners from the data by adjusting its internal parameters to minimize errors. However, to achieve the best performance, which uh, you can adjust, we call hyperparameters. These are the external settings like learning rate, model complexity, must be carefully tuned by you or developers, often through measures like how to identify those hyperparameters or the right parameter value. You can use methods like grid search or randomized search using validation data, uh, which we already discussed. So the evaluation on unseen test data is how model evaluation happens, how will the model generalize beyond its training data is how you do the evaluation. So this is it. If you have any questions, you are welcome as well. Okay. Is that clear? Okay, thank you, Jala. Any confusion? I think it would be easier for you guys to understand it because you already are familiar with modeling. So I'm assuming it's easier for most of you at least. Okay. If you have any questions, all right. So if you don't have any question, I don't have to hold you on the session. Just can I get a final reaction that you have understood and we can move on? Great. Then I'll start the recording.